For our last talk today, we're very happy to have Davison from Edinburgh, who will tell us something about this topic.
Yeah.
Welcome to the south.
To the Midlands, surely. Yeah, okay, well, thank you very much for the invitation. It's actually my first ever time in Birmingham, so I'm unusually excited. So obviously my first time here. Thanks for inviting me to this very fun conference. I'm afraid my talk is not really so much about enumerative anything, though the techniques in it, the background, they're all inspired by results in Donaldson-Thomas theory, which is very much an enumerative theory. Before I get going, how is that for size and legibility? I mean, it might degenerate over the course of the talk, so do shout at me if it becomes illegible. Yeah, okay, so the talk is about Nonabelian Hodge theory for stacks. So I'll recall this in more detail over the course of the talk, but the classical Nonabelian Hodge correspondence is a homeomorphism between the classical topological spaces underlying two moduli spaces, parameterizing moduli of objects associated to either a Riemann surface or a smooth projective curve. And the point of this talk, the point of the results I'm going to present, are an upgrade of this to some kind of correspondence between moduli stacks. And it's going to turn out that I can't give you a homeomorphism between the corresponding moduli stacks, but I can give you an isomorphism in something called Borel-Moore homology, which is a topological invariant of those stacks. So that's the place we're heading, and I should say this is joint work with Lucien Hennecker and Sebastian Schlegel Mejia, both at the University of Edinburgh. Okay, so let's fix some background objects. So C for me will be a smooth projective complex curve. And in the first part of the talk, I'm going to introduce the kind of classical players, the classical moduli spaces that one associates to this curve as a route to reminding you or telling you for the first time what the Nonabelian Hodge correspondence is. So the genus, there are essentially three different cases. There's genus 0, genus 1, and genus greater than or equal to 2. And genus 0, for the purposes of this talk, for the purposes of what I'm doing in this talk, will turn out to be trivial, but worth recalling and staring at and trying to gain some kind of inspiration from. Genus 1, for the purposes of this talk, will be highly non-trivial, but at least sort of done in the past. And this is where the new results are. And this is a sort of common trichotomy in the subject that genus 0 is trivial, genus 1 is difficult, and genus 2 is a zoo. So let me start on the Dolbeau side. So what people mean by the Dolbeau side is the moduli space of Higgs bundles. Okay, so definition. A Higgs bundle on C is a pair. Curly F, and then eta going from curly F to curly F tensor with the canonical bundle of C, where F, I'm going to ask, is a locally free coherent sheaf. aka a vector bundle, depending on your upbringing. Yeah, this is what's called the Higgs field. And don't ask me what it's got to do with anything, really, with why it's called that, because I still haven't done that particular piece of homework. Yeah, so the rank, or the R of this F, so actually, let me put a tilde over an F to mean that it's a Higgs bundle, and the underlying F is the underlying coherent sheaf. So the rank of a Higgs bundle is just the rank of the underlying coherent sheaf, and the degree of a Higgs bundle is the degree of the underlying coherent sheaf. And the slope, slope of a Higgs bundle, somewhat unexcitingly, is the slope of the underlying coherent sheaf. So this is RF over dF. And I should say there is a version of the theory where we don't ask that F is locally free. There's a version of the theory where, in fact, you can allow F to be a torsion sheaf supported on a zero-dimensional subscheme, and there are interesting things to say there. But I'm not going to talk about that today. Right, and I've got enough space here. F is called semi-stable if for all non-zero sub-Higgs bundles, proper sub-Higgs bundles, G tilde, the slope of G tilde is less than or equal to the slope of my original Higgs bundle. And as usual, stability is the request that this inequality be strict. So I can do this. Not sure how well that works with my penmanship skills, but yeah. So really, I'm interested in semi-stable Higgs bundles. Right. And throughout the talk, I'm going to use the letter X to denote coarse moduli spaces. So X will always be an algebraic variety and not a stack or anything like that. And let's see. So X, R, D, C. This is the moduli space. So coarse moduli space of degree D, rank R, semi-stable Higgs bundles on C. And yeah, I'm always going to use M to denote stacks. So M, R, D, C. Yeah, sorry, what do I want to do? I'm going to put a doll here to remind us that we're looking at the Dolbeault moduli space. This is the moduli stack parameterizing the same objects. Okay, so points in the scheme, or complex points in the scheme, are in bijection with polystables of degree D, rank R. That is direct sums of stable Higgs bundles of the same slope. In particular, not all semi-stable Higgs bundles will actually make an appearance in this scheme in general. Only the polystable ones. Whereas this is somehow better. This here, the points really correspond to. Points in this really correspond to semistable Higgs bundles of degree d and rank R. And because it's a stack, it also remembers the automorphism groups of those points. So that's somehow the beauty of stacks, that you find all of the objects in your category in there, and also the geometry remembers the automorphisms of those objects. So rather than try and drag anyone with me who has never seen a stack before by defining them or doing anything bonkers like that at this time of day, let me just illustrate this with an example. And let me go to my example that I claimed was trivial. If I write down here, is that any good? Or okay, see if my knees are still working. Yeah, so let's do the genus 0 case, and let's set the degree to be equal to 0. Okay, so here it's possible to show. Well, maybe I can give a sort of one-line proof. So say I have, so here, because the genus is 0, my underlying curve I can just take to be P1. If I have any vector bundle on P1, by Grothendieck's theorem I can write it as a direct sum of line bundles. So my Higgs bundle, the underlying coherent sheaf, will look like some direct sum of twists, Serre twists of the structure sheaf. So I equals 1 to R. But one can show using semi-stability and the fact that the canonical bundle on OP1 is anti-ample, that actually all of these shifts have to be trivial, which means I can, if I find the eraser again, I can just ignore, just delete this. And my Higgs field, so my underlying coherent sheaf is forced to be R copies of the structure sheaf. And because there are no global sections of the canonical bundle, again, we only have one choice for what the Higgs field is. It actually just has to be 0. It's the only semistable rank R degree D Higgs bundle. Okay, so it's a polystable. It's the direct sum of R copies of the same objects, but with R replaced by 1. And so what we find is that X dol C R 0, this is just a point. So some corroboration of my claim that in genus 0 things are going to be quite boring in this talk. But at least for the stack, still it's only going to have one point. There's only one semistable. But that point is going to remember the automorphism group of this Higgs bundle. And that automorphism group is, you can see, is just GLR. So this is going to be what's known as the global quotient stack of points modulo GLR, or to put it in a way perhaps more familiar to topologists, BGLR. So this is just point GLR. Okay. Okay, yeah. So that's all I want to say about the Dolbeault side for now. Any questions? Hopefully nothing too controversial has gone up yet. So, yeah, so the same back of envelope reasoning that you do to show that the only semistable Higgs bundle in degree 0 is this one will tell you that if you set D to be anything other than a multiple of R, there are no semistable Higgs bundles. And if D is a multiple of R, let's say it's 5 times R, the only semistable Higgs bundle will be R copies of the 5th Serre twist of the structure sheaf with 0. when did I start? Doesn't matter. I mean, about 15 minutes ago. There's Prosecco waiting for us, Michelle. People are going to lose their patience. Okay, so that's the Dolbeau side concerning Higgs bundle. The Betti side is somehow more simple-minded. So for the Betti side, I take my complex curve, I take the underlying classical space, and that's all I remember. So yeah, I think I just want to. What do I want to do? Yeah, so let sigma g be the underlying classical, i.e. not Zariski, topological space of C. So in other words, I take C, I consider it with its analytic topology, and I just take the underlying topological space of that. And I'm going to make my life difficult, I'm going to pick a point which I must never call P. Let's call it alpha. A point in here, and I let sigma g prime be sigma g, but punctured, so I take away this point alpha. And yes, so I'm going to let x Betti R D be the coarse moduli space of R-dimensional representations of the fundamental group, the fundamental group of this punctured Riemann surface, such that the monodromy around the puncture is given by multiplication by, so I fix, a primitive rth root of unity, and I raise it to the power of d. Okay. So a couple of remarks about this. One. So the case d equals 0 will play a special role in this talk. So it's somehow the most difficult and the most natural case, as far as I'm concerned. So here, what happens if I set d equals 0, and also the most singular. That will become evident. So if I set d equals 0, then I'm asking that the monodromy around the puncture actually be multiplication by the identity, which is like saying that the local system extends over the puncture, which is saying that my representation of the fundamental group of this punctured Riemann surface is secretly a representation of the fundamental group of the unpunctured Riemann surface. So in this case, XR0 Betti, this is really the coarse moduli space of pi 1 sigma g reps. So that's, again, some corroboration for my claim that that's somehow the most natural choice of D. And two, the points of X, B, R, D are in bijection with, again, I should have said isoclasses over there, I didn't. Isoclasses of semi-simple pi 1 sigma g reps satisfying the monodromy condition, which I won't rewrite. Okay, so this is a nice scheme. In fact, one can show that it's an affine scheme. So in some ways, it's easier to get your hands on than the corresponding object on the Dolbeaus side. And just as on the Dolbeaus side, for me, the more interesting object is the stack. So this is just the stack of, am I going to rewrite this? Yes. R-dimensional reps of pi 1 sigma g punctured. And again, the dot 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 means satisfying the monodromy condition. And here, the points are, or the isoclasses of points are in bijection with the isoclasses of all modules, all R-dimensional modules. And again, dot 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 means satisfying the monodromy conditions. And there's a morphism that goes from here to here called JH. And at the level of points, JH sends a modular or representation rho to the semi-simplification of rho. So it's an undergraduate result that rho has what's called a Jordan-Holder filtration, and while the Jordan-Holder filtration isn't unique, the set with multiplicities of the subquotients appearing in that Jordan-Holder filtration is well defined, and that's the semi-simplification of rho. Maybe I should add that there's an analogous map here which takes a semi-stable Higgs bundle to something called its semi-simplification. Okay, and I have enough space here to keep abusing the g equals 0 case. So if g equals 0, and again, let me focus on... Oh, this is... There I was wondering who hasn't muted their iPad, and it's me. But it's Siri telling me about an upcoming film. Okay, whatever. So if g equals 0, then I'm looking at the fundamental group of P1, which of course is just trivial. R-dimensional representations of this group, that's the same thing as a R-dimensional vector space. So in particular, there's only one of them. X, R, D. Up to isomorphism, there's only one R-dimensional vector space. But that R-dimensional vector space, its automorphism group is GLR by definition. So the stack is point mod GLR. And this JH map is just the structure morphism. It's the only morphism that goes from here to here. Something a little bit suggestive has happened in that we've found for genus 0 the same varieties on both sides. So the coarse space is just a point, and the stack is point mod GLR, where R is one of the two invariants of our moduli spaces. Okay, and right, so. No, the punctured case is the background case. If D is equal to 0, then it reduces to the unpunctured case. Because if D is equal to 0, then the monodromy around the puncture is trivial. Okay, all right. I'm not sure how helpful this will be, but it's easy to check, or easy exercise, or whatever. The fundamental group of the punctured Riemann surface of genus G is actually the free group. One can see that by realizing the genus G Riemann surface as like a 2G gon, where you glue the sides and then you puncture it, and that means you can rip out the 2 cell. And so to look at representations, yeah, and this, let's call L the loop around the puncture. In the sort of standard presentation of this fundamental group, L is equal to the product of the commutators AI, BI. I goes from 1 to G. And so to ask that the monodromy around here is trivial, i.e. to ask that this acts trivially on my representation, is to ask that this product of commutators act trivially, which is the same thing as saying I'm looking at a representation of this group modulo this relation, which is the standard presentation of the fundamental group of a genus G Riemann surface. I hope that helps. Okay, yeah, so the classical Nonabelian Hodge theory, or classical Nonabelian Hodge correspondence, due to lots of people, Ouellette, Hitchin, Donaldson, Simpson, and this is presented neither in alphabetical nor chronological order. It says the following: there is a homeomorphism. So there exists a homeomorphism. And this homeomorphism is canonical once you make certain extra choices. At the level of the coarse moduli spaces. And I can't emphasize that enough. It's something about the coarse moduli spaces, not about the stacks. So it goes from X, dol, R, D, C, to X, Betty, R, D. Okay, where this thing depends on G, the genus of C. Yeah, so this is as topological spaces. So to give you an example, let G equal 1 and R equal 1, and D can be anything. Then one finds that X dol R D C is the total space of the cotangent bundle to C, where C is here an elliptic curve, and X Betty R D is isomorphic to the Cartesian square of C star with itself. So these are homeomorphic as topological spaces, but completely different as algebraic varieties. This has in it the zero section, which is a projective subvariety, and this is affine, so it's got no non-zero dimensional projective subvariety. So they're really different as varieties, but the same as topological spaces. You can think of this as S1 cross S1 cross R, and you can think of this as S1 cross S1 cross R cross R. Okay. Any questions about that? How? Using a lot of very difficult infinite dimensional harmonic analysis. Yeah, I mean, it's explicit what you do. It's explicit the equations you solve, but they're very, I mean, as indeed they must be, given what the theory spits out. They're very far from algebraic. Okay. So, yeah, as trailered, I'm especially interested in the d equals 0 case. And I'm going to concentrate on this for the rest of today, for the rest of the talk. So here, if the genus is greater than or equal to 1, and R is greater than or equal to 2, then the moduli spaces, both at the level of stacks and coarse moduli spaces, are singular. So the genus equals 0 examples that I got up on the board are somewhat atypical, as is the R equals 1 example over here. For basically any other choice, you get something singular. Okay, so if X is, okay, so just to start off with some notation, if X is a smooth variety, so I bundle into my definition of variety that X is equidimensional, then I denote Q var X. This is just the locally constant sheaf on X with coefficients Q, but I shift by the dimension of X, which makes sense because of my assumptions on what a variety is. And yeah, so why choose this? This is Verdier's self-dual. It's Verdier's self-dual, and it's a perverse sheaf. And yeah, perverse sheaves are going to make a sort of fleeting appearance in this talk, and if you know them and love them, that's great, and if you don't, then you can sort of black box any reference to them. Okay, so that's just notation. Now, if X is not smooth, so it's singular, and do I have enough space? Yes. There are, I claim, at least 3 sensible ways to extend Q X on the smooth locus shifted like so to the whole of, to a sheaf on the whole of X. So let me list them. One, well, probably the most obvious, I suppose, is just take the constant sheaf on X shifted, because I've got my shift in here, and that restricts to this thing, and you know that's perfectly legitimate. Now let P, that's why I didn't use P earlier, be the structure morphism for X, and let's say I apply P lower star to whatever I've got here, and by P lower star I mean derived P lower star. So if I take derived global sections of the constant sheaf, that's a kind of semi-modern way of just defining what singular cohomology of X with coefficients in Q, but shifted just because I've shifted everything. That's, you know, you could actually define this way. So that's one way you could extend this shifted constant sheaf to a sheaf on the whole of X, or a complex of sheaves on the whole of X. So I've noted in passing that this thing is Verdier's self-dual. So I could extend its dual, and the natural way to do that is you just take the Verdier dual of the constant sheaf on X, and the ver here is this shift. Okay, so this is the constant sheaf on X, and I take its Verdier dual. If I take the derived global sections of that, I get what's called the Borel-Moore homology of X. And as throughout the rest of the talk, there's a shift here. So if Verdier duality is unfamiliar to you, let me just tell you a few things about it. It's just some anti-equivalence on the category of complexes of constructible sheaves on X, such that, and here's the key thing, whenever you have a functor with a star, you can push D past it at the expense of turning that star into a shriek. So what that means is that, let me just do a little calculation down here, P lower star Verdier dual is the same as the dual of P lower shriek of Q. And the duality functor on sheaves on here, aka vector spaces, is just the dual of vector spaces. P lower shriek of the constant sheaf is just a way of defining what the compactly supported cohomology is. So one way of thinking what this Borel-Moore homology is it's just the vector dual of compactly supported cohomology. So that's another way of extending the shifted constant sheaf to a sheaf on the whole of X. And this is what you get when you take derived global sections. And then 3, because I forewarned you there would be some perverse sheaves in this talk, there's a sort of natural minimal way to extend this to a perverse sheaf on the whole of X, and it's called the intersection complex on X. And this is the unique simple perverse sheaf on X which restricts to this shifted constant sheaf. And if I take the derived global sections, I get, again, a sort of fairly modern way of defining what the intersection cohomology of X is with this shift thrown in. Okay, so each of these 3 have their plus points. So the plus point to this is that it's fairly natural. Fairly natural. But that's the only good thing I'm going to say about it. It's going to turn out that in the context of this talk, it's actually quite a bad choice. So that's all I can say about that. 2 is somehow better. It records more data about the singularities. This is really a phenomenon that appears when you're looking at singular non-projective varieties. So a very easy way to cook up one of those is just take any projective variety and take the cone over it. And that will automatically be singular unless, I guess, your original variety was a affine line or something. And yes, consider the cone over your variety. And now take its singular cohomology. It's very boring because I can contract that cone down to a point. Whereas the Borel-Moore homology, or the dual compactly supported cohomology, will record a lot more of the topological data of your singular variety. And the kinds of varieties and stacks that we're going to meet in this talk are all going to be singular and never projective. So this is worth taking note of. And 3, I don't want to say much about it right now because I'm aware that not everyone in the room will have met intersection cohomology before, and that's fine. But I just want to say this is somehow I can't really spell this word. This is the connoisseur's choice. If you do enough research in geometric representation theory or the Hitchin system, which is the study of the push forward of the constant sheaf from the Dolbeau modular space down to the Hitchin base, you have to run into these, and your answer will be written in terms of these. So, this is somehow the right thing to consider or appear, but for now I'm going to ignore it, and it's just going to, force an entrance later on. Okay, so, this is the topological invariant that I'm going to try to understand. Yep. Oh, and as a remark, they all agree if X is smooth. Okay. Are there any questions while I do this?
Just about the Langland program, where does it fit? Is there one equation?
it would take me quite a while to build the bridge between what I'm talking about right now and Langland's program. But
no bridge, just
equation.
equation.
I'm not sure what you mean. Okay. Yeah, so to carry on flogging this dead horse. So in G equals 0, we saw that all of the stacks were smooth. So on the Dolbeau side, so let's pick R to be anything greater than 1 and D to be 0. I've said it, but I'll say it again. This is somehow what you do to get the most singular and stacky behavior. On the Dolbeau side, we found, the Nonabelian Hodge correspondence, the homeomorphism at the level of coarse moduli spaces, not saying anything very interesting. It's saying that a point is homeomorphic to a point. But we found that we could do better. We found that the Dolbeau stack RDC is isomorphic to point mod GLR, which in turn was isomorphic to the corresponding Betty. Oh, whoops. I've broken my one rule. Yeah. No, it's fine. Well, actually, is this becoming faint?
It's becoming a bit hard to read on the video.
Fine. Thank you. Okay, so so they're actually, they're basically the same topological stack on both sides. So in particular, any topological invariant that I care to extract from that stack will be the same. So we get that the Borel-Moore homology of M dol R B C Q, and this verse shift ends up being anyway, whatever. I'll put it in. This is isomorphic to the Borel-Moore homology of the corresponding Betty stack. Okay. And it's not very enlightening. Of course, they're basically the same topological space, so of course they have the same invariance. And the point of the rest of the talk, how long have I got? Okay. The point of the rest of the talk is going to be that somehow it's hopeless to find an isomorphism like this in general, but I'm going to try and find an isomorphism like this between the Borel-Moore homologies of these stacks for higher genera. Okay, so let me, because I'm running slightly low on time, let me do genus 1 as an aside. Like I say, this is somehow done, but non-trivial. And what one finds is the following. If I take the direct sum over all R greater than or equal to 0, so for R equals 0, the stack will be a point. Somehow forget about R equals 0. Of the Borel-Moore homology of the Dolbeau moduli stack, rank R, degree 0, semi-stable Higgs bundles on Q with the appropriate shifts thrown in. This, one can show, is isomorphic to the free supercommutative algebra generated by an infinite number of copies of the cohomology of T star C Q. Again, there's some shift here. Tensored the cohomology of B C star. Okay, and this I want to think of as being a bigraded vector space. It has grading coming from this decomposition according to R, and it has a cohomological grading. Similarly, this space that goes in these brackets has a bigrading by R and by cohomological degree. And if I have a bigraded vector space and I take the free supercommutative algebra generated by it, that inherits a bigrading. And this is an isomorphism of bigraded vector spaces. Similarly, if I take the direct sum over all ranks of the Borel-Moore homology of the Betti stack with the appropriate shifts thrown in, this is isomorphic to the free supercommutative algebra generated by an infinite number of copies of the cohomology of C star squared with appropriately shifted coefficients, tensored cohomology of B C star. Okay, so this is some huge bigraded vector space. I take the free supercommutative algebra generated by it, and then if I take the rth piece of whatever that is, I get the rth piece of this. Now, this huge bigraded vector space is isomorphic to this bigraded vector space because the cohomology of C star squared is isomorphic to the cohomology of T star C. So when I take the free supercommutative algebra generated by these two isomorphic things, I get isomorphic things, which gives me an isomorphism between these two lines of graded vector spaces. And so in particular, if I just fix a graded piece, i.e. I fix an R, I get an isomorphism in Borel-Moore homology between the stacks. So this tells us that this hope that I could extend this isomorphism in Borel-Moore homology beyond genus 0 is not so abject that it might be doable. And the rest of the talk will be the new stuff, will be genus greater than or equal to 2. And maybe the aside was presented very quickly, so I'm not sure how much that would have gone in. But maybe the moral of the aside is that it doesn't make sense to fix R. And this happens a lot in enumerative geometry, so that's my one callback to what I'm actually meant to be talking about. Like partition functions. If you ask the question, how many partitions are there of a certain natural number n, give me a formula for that, that's somehow the wrong question. The right question is, can you provide me with a generating series such that the nth coefficient is the number of partitions of n, and then you've got the Euler product form, and everything becomes very beautiful. Something similar has happened here, that if I were to extract from this the actual isomorphism class of the rth piece by taking a whole bunch of direct sums of symmetric tensors, it would be a horrible mess. But taking everything together makes life easier. Okay, so let me present the solution to this problem in the... Hey, yeah. Well, I mean, this thing is always the classical truncation. In fact, both of them are the classical truncations of zero-shifted symplectic stacks. So there's a lot of symplectic geometry here. Always, yeah. Yeah. Okay, so in the remaining 10 minutes or so, let's get to the solution. So let's recap the problem. Well, we have a kind of bottom row, x, r, d, dol, c, x, b for Betti, r, d, and we have the classical Nonabelian Hodge theory isomorphism that goes from one to the other. And we have the corresponding moduli stacks, the Betti stack, RD, and we have these vertical maps which are the kind of semi-simplification maps. For those that have done lots of GIT, one way of thinking of what this map is it sends a semi-stable object to its S-equivalence class. And we would like, we could have maybe one day dreamt of having an isomorphism that goes along the top row that makes everything commute. That would be great, and we could definitely go home happy. And as I've hinted earlier in the talk, that's just not going to happen. So I'm not going to be able to, I think I've already used alpha, haven't I? I'm not going to be able to find alpha for you, or beta, as it's now become. But I am going to try to construct for you H, B, M of beta. This is what I want to find, an isomorphism in Borel-Moore homology. Okay, so there's not actually going to be any beta that I apply this functor to, but there is going to be this kind of composite object, which is going to be an isomorphism in Borel-Moore homology.
Question? Is it known that beta doesn't exist?
This is slightly thorny. So there's a remark in Simpson's second representations paper, which, I don't know, I read through the remark as a counterexample, but then he ends the remark by saying it's still worth thinking about. But it's, let's say what he proves is that there definitely isn't a natural, sensible way of constructing beta. And if you try the natural route, you will fail. Something will go wrong. Even for rank 2, it's just rank 2 Higgs bundles over an elliptic curve. There's already a sort of what looks like a terminal obstruction to constructing beta. Okay. So how am I going to do this? So recall that Borel-Moore homology, this is the derived global sections of the dualizing complex. So I'm not going to be able to construct this isomorphism, but I do want to construct this isomorphism here. And the way to do it is, so let me now give this a name. The strategy is the following. Is to construct an isomorphism between the push forward along this isomorphism here of the push forward or direct image along JH, and maybe I should put a D here for doll, B here for Betty, of the dualizing complex appropriately shifted. Find an isomorphism between that and the push forward along this vertical map of the dualizing complex on this stack. And this is somehow better than the thing I set out to do, and I can get this isomorphism by then just taking derived global sections applied to this isomorphism. That sounds like a great thing if it can be done, but how to achieve one? To do this by understanding JH lower star applied to the dualizing complex with whatever the appropriate shift is, where M here, so understand this very well. I have a completely explicit formula for what it is for M, a general 2CY category. And I'm certainly not going to explain what a 2CY category is, except to say that the category of degree 0 semistable Higgs bundles on a curve C and the category of representations of the fundamental group will be two examples of a 2CY category. So Higgs bundles with some conditions, and reps of pi 1 sigma g. Okay, so I've got 5 minutes to do that. Okay, so the way to do this is we start off with the decomposition theorem. For 2 CY categories. And that says the following. If M mapping along a morphism which, in keeping with the rest of the talk, I'll call JH, mapping to X, is the morphism from the stack of objects X in some 2 CY category curly C to the coarse moduli space, or the good moduli space, in more precise terminology, then the decomposition theorem holds in the following sense. If I take the derived push forward of the dualizing complex on this usually very singular stack, this is pure. And what that means is that it's isomorphic to its cohomology with respect to the perverse T structure. So it's isomorphic to a direct sum over I of its ith perverse cohomology and I shift. So this push forward. Sorry, I've left out some symbols. This push forward is a huge complex in this category of perverse sheaves or constructible complexes, and so it lives in the derived category. And as you may or may not know, usually if I have some object in the derived category, or if I have some complex, it's not actually quasi-isomorphic to its cohomology sheaves. This is something called formality. Usually it doesn't hold, and what the first part is saying that it just does hold here. And I can even improve upon this slightly and say that the direct sum is not over all I, but over even non-negative numbers. And each of these perverse cohomology sheaf is pure, so it's a direct sum, and each cohomology sheaf is a direct sum of intersection complexes. Okay, and so we've reduced the problem to working out what are the summands that appear. So if I isolate a perverse cohomological degree, write this thing as a direct sum of intersection complexes, I need to work out the supports of those complexes and the monodromy. And this is this is a game that people have been playing for 20 years with the Hitchin fibration, and so we should be good at it by now. And let me finish by sort of explaining how to win the game for this particular case. So it's easy when you know how to show that the intersection complex for the coarse moduli space, so the connoisseur's choice of the way to extend the constant sheaf from the smooth locus, is a summand of the zeroth perverse cohomology. Okay, so on the base, I have the intersection complex, and that appears in the zeroth perverse cohomology of this push forward. And then, much less easy, is to use Hall algebra techniques to show that JH a star of the dualizing complex on the stack with its appropriate shift is an algebra object. And to explain what an algebra object is, I have to give you a tensor structure on the category of complexes on the base. And that goes as follows. So remember, X represents polystables or semi-simples, i.e. direct sums of simples or direct sums of stables. And in particular, if I have a pair of such objects, I can just take their direct sum and get a new such object. And I define F tensor G to be the exterior product of F and G. If F and G are sheaves on X, I can take their exterior product to get a sheaf on this Cartesian product and then push it forward along the direct sum map to get a new sheaf here. And it's with respect to that tensor structure that this is an algebra object. And so using these two observations and a little bit more, we get a morphism from symmetric tensors in the intersection complex on the whole base under some conditions which I will make clear. I get a morphism from here to here. This is assuming that C is totally negative. So that's some condition on the Euler form, which in the context of this talk corresponds to genus greater than or equal to 2, i.e. all of the remaining cases. And the theorem, which is joint work with Lucien Hennecart and Sebastian Schlegel-Mejia, is that this is an isomorphism. Okay, so if we come back to our problem and our strategy, we're trying to show that this thing is isomorphic to this thing, but we can use our theorem twice to show that this thing is some massive symmetric algebra. I've misstated the theorem, sorry. That's what happens when you don't manage your time properly. Sorry. There's some extra wrinkle there. But the point is that we can explicitly describe this push forward in terms of the intersection complex on the Dolbeau moduli space. And on the other side, we can express this push forward as some massive thing built out of the intersection complex on the Betti moduli space. But psi is a homeomorphism, so it sends the intersection complex on the left-hand side to the intersection complex on the right-hand side. And so as a corollary, which I'll put here, this isomorphism, which I'll call capital phi, exists and is canonical. So in particular, as I say, applying the derived global sections functor to phi, I get the isomorphism in Borel-Moore homology. And that's a good place to stop. Thank you very much for your patience.
Questions? Comments?
In the theorem, you don't fix the line. That's important.
Yeah, that is important. So I didn't fix the rank. I took all ranks at the same time. Yeah, and yeah, it's important all the way through. So here I obviously can't fix the rank because the rank is additive under direct sums. So yeah.
What are these all algebra? I mean, I know how algebra works. Is that
So I have my moduli stack of objects in my category, call it C. So this is a very, very blurred version of what we do. I take the stack of exact triangles of objects in C. I have a push forward from here to here. So this is exact triangles. 0 goes to rho prime, goes to rho, goes to rho double prime, goes to 0. This is the this sends such an exact triangle to rho prime, rho double prime. So it just remembers the outer two terms, and then there's a third map which remembers the middle term. And the basic idea always, though there's always some kind of complication and problem you have to solve, is to construct a pullback and a push forward map in whatever cohomology theory you're considering, and in that way get a morphism from the tensor square of the cohomology of your stack to the cohomology of your stack, i.e. an algebra structure on whatever it is you're trying to study. But the kind of dumb observation is that I can complete this diagram like so, where this is my direct sum map. So this, again, is an undergraduate exercise. If I take the semi-simplification of something that appears in the middle of a short exact sequence, it's the direct sum of the semi-simplifications of the terms on the extremes, which is another way of saying that this diagram commutes. So whatever algebra structure I built on the cohomology of my stack, it lifts to an algebra structure on the push forward of the constant sheaf, or the dualizing complex in this talk. That push forward down to XC, just by the same, by the same definitions.
I have another question, which is, what's the progress on like the wave filtration, filtration?
Well, there's been lots of progress on that. So two independent. So so that's a conjecture, or no longer a conjecture, a theorem that is specifically about the smooth moduli spaces. So it's related to what I'm talking about today, but it's a little bit different. So the theorem proved by Maulik and Shen and Mellet, Schiffman, Minetz, Hausel, is that the weight filtration on the Betty side goes to the perverse filtration on the Dolbeau side for the case where R and D are coprime, i.e. the smooth case. But there's a separate conjecture due to De Cataldo and Maulik, which says that the weight filtration on the intersection cohomology of the X, so the singular Betty coarse moduli space is twice, it's the same as once you double the indices, the perverse filtration on IH star X dol R0 C Q, and in a way that would take too long to explain. What I've presented today gives a way to interpolate between the classical, or the oldest P equals W conjecture and this conjecture, which is called the PI equals WI conjecture. in the sense that the intersection cohomology obviously features in this talk, because in the end we reduce everything to understanding the cohomology of intersection complexes, i.e. intersection cohomology. The old moduli spaces, the smooth ones, make a kind of unexpected appearance via something called chi-independence. And yeah, using these facts, you get between the two conjectures in a way which still has a slight hole. So I can't actually prove the pi equals wi conjecture, but this is a sort of very promising route to try and do so. Yeah.
More questions?
So, in the end, to be the isomorphism, you need the classical.
Yeah, exactly.
There's no way around all the analytic techniques.
Not that I know. Yeah. Yeah.
And so, this decomposition theorem for the push forward.
Yeah.
So, in particular, it is like a direct sum of simple things.
Yes, shifted simple things.
Shifted simple things.
Yeah, cohomologically shifted simple things.
Should this be true for all like with moduli space? Because it's like those
No,
because it's super proper map.
Yeah. So if this was a pure mixed Hodge module, then using the fact that that morphism is approximated by proper maps, you would get a quick proof of the decomposition theorem. Is that what you're referring to?
Well, I guess I was asking if you have a good moduli space of the stack,
Yeah.
then it could push forward above to it's a direct sum of simple.
Yeah, I think this is quite special. What's true and non-trivial is that if I have a pure mixed Hodge module on a moduli stack that has a good moduli space and I push it forward, it will satisfy the decomposition theorem using the fact that this morphism, which I've called JH here, it's not projective, but it has this strange property of being approximated by projective morphisms. But in very simple examples, for very simple 2CY categories, it's possible to show that this mixed Hodge module is impure. So that strategy doesn't work here.
Couldn't Becky cohomology be expressed in terms of double homology based on the equations that we've actually got on the board?
Well,
Could you get an equation that defines Becky cohomology using double homology?
yeah. I mean,
what C is north of one? I don't know.
well, I mean, yeah, just for the avoidance of any doubt about what I'm saying, the upshot of the whole talk is that in Borel-Moore homology, I have an isomorphism. So, and this is the main point of the talk. I mean, if the question is what happens if I remove the letters BM from here, I don't know. I've got no idea.
Was it important that D was 0 or that was just
No, it's not important. It's the point of picking D equals 0 is that it's the hardest case. It's the most singular, most stacky case. So if you can do it for D equals 0, you can do it for everything else. And so the point is, instead of, I mean, it would add 10 minutes to the talk to take care of all D, and I just want to jump to the one, like the sort of end of game boss, just defeat that immediately and then leave the rest of the intermediate stuff. But yeah, no, this, I mean, what I've written here does not need D equals 0.
So that really expresses not like an isomorphism, but just an equivalence class of
Oh, you might have to repeat the question.
I mean, it's beyond my ability, but I mean, I feel like you're not necessarily, from that last formula, you're not describing an isomorphism between Davison and Betty's homology. You're just maybe like an equivalence of categories that those, if you like, functions living with.
I'm not sure if it's related to your question, but I mean, as an aside, I think it's quite late in the day for asides. But yeah, Simpson does actually show that the category. So if I take the points corresponding to objects in here, you know, they correspond to objects in a category, and that category is equivalent to the corresponding category over here. So it's kind of unbelievable that it should be impossible to find this isomorphism, given that we know that the underlying categories are equivalent. You know, I mean, somehow it sounds like just a mistake. Like if I have two equivalent categories and I take the moduli space of objects in those two categories, they'd better be equivalent to stacks. But something subtle goes wrong. Yeah, and that's why this talk exists. Sounds good.
Yeah, thank you so much.
No problem.